Chapter 11, acids and bases. We are going to rush through this, get through it as quick as possible. That means I'm taking out all the fun stuff like logarithm rules and how we derive some of the logarithm-related equations that we'll see towards the end. We've encountered acids in lab, and I think a little bit in lecture as well. Acids are found in a lot of foods, like lemons and limes, which are fast. Acetic acid is also present in vinegar, and tartaric acid is one of the acids that they use to coat sour candy. Think Sour Patch Kids. The way that acids work is they combine with saliva in your mouth and they produce H+ ions. Those H+ ions, we'll see that information again later, those H+ ions react with protein molecules on your tongue and they send an electrical impulse to your brain that tells you that's a sour taste. What can we learn from this? Protons, H+ is just a proton. Protons are sour. Some of our acid properties. Acids have a sour taste and dissolve many metals. We love technology failing the last day of lecture. This is like when the avatar vanished. Okay, we're back. So properties of acids, they have a sour taste, they dissolve many metals. They also turn blue litmus paper red. That's not really that important, but that's a thing. Here's a bunch of examples of acids and where they're used. There's also bases. Bases have a bitter taste. Bases also have a slippery feel. And they're the opposite of acids in that they turn red litmus paper blue, which is not that important. So they have a slippery feel. They combine with oils on your hands to make soap, and that's why they feel slippery. Bases have traditionally been used in soap making, and they also have that bitter taste. Things like Drano and tonic water. Tonic water contains quinine, which is a base. Drano you shouldn't be drinking. You can drink tonic water. These things contain bases. These are stuff that you can buy at the store. Bases are less common in foods. Alkaloids, things that contain nitrogen, are organic bases that are found in plants like hemlock. These are often poisonous, and the bitter taste tells us, hey, don't eat that. That's something that's like ingrained in us for hundreds of generations of being alive on the earth. Things that are poisonous tend to be bitter, and so if you eat something bitter, that's a good sign that you shouldn't be eating it, except for coffee. Coffee also has some bases in it, like caffeine, that impart a bitter flavor or can impart a bitter flavor, and we should be drinking coffee. We should be drinking coffee because it's yummy. And we like the way it makes us feel. Also some more bases and stuff. All right, our first set of definitions. Our first set of definitions are from the Swede, Arrhenius, the Arrhenius definition of acids and bases. Acids produce H+ in aqueous solution. So there's two important components to our Arrhenius definition. They produce H+, and specifically in an aqueous solution. An aqueous solution means that water is our solvent. That's what we're dissolving the things into. Chemicals like HCl are covalent compounds. They don't contain ions. It's two nonmetals bonded to each other. If you put HCl into water, it forms H+ ions and Cl- ions. H+ ions in water makes it an Arrhenius acid. Something about the angle today. Unplug, replug. The screen went out again. We're back. We're so back. Right, so you put HCl in, it produces H+, and water is what's dissolving it. H plus ions, however, are highly reactive. So in aqueous solution, in a water solution, they bond to water molecules like this. One of these lone pairs goes over and grabs that H plus, and it forms a bond. And now instead of 2 H's and an O, you've got 3 H's and an O, and a 1 positive charge. H3O plus is the hydronium ion that showed up on our nomenclature. I believe that was one that was on there. In water, H plus ions are always going to associate with H2O molecules. They're never going to be found alone. We'll often use H plus and hydronium interchangeably. So if we're talking about H plus and we're in an aqueous solution, you can assume that that's actually H3O plus in solution. We're just simplifying it by removing the H2O part. One of our telltale signs of an acid is that the ionizable hydrogen comes first, aka the removable hydrogen. The removable / acid hydrogen comes first, is written first. That is true for this class. That's also often true outside of this class. It's not always true outside of this class. Like acetic acid in vinegar, H, C2H3O2. The H in front means that we've got an acid, and it means that we've got one ionizable hydrogen. There's only one H in front. That's the only hydrogen that pops off. These other 3 hydrogens stay connected. It's part of our acetate ion. So our structural formula can show us how the atoms are bonded together. Our molecular formula just indicates how many of each type. In HCHO2, it's this hydrogen that's ionizable. This hydrogen can come off. This is the acidic hydrogen. You don't need to know the structural part of this, but if you're wondering, that's the one that pops off. So it's an acid because hydrogen comes first. The hydrogen that comes first is the one that can be released in solution. So that's our Arrhenius definition for acids. Our Arrhenius definition for bases is similar. Bases produce hydroxide. In aqueous solution. So our 2 key components for an Arrhenius base is they produce OH minus hydroxide in aqueous solution. It's got to be a water-based solution. It's got to produce OH minus. So things like sodium hydroxide are Arrhenius bases because it dissociates. It's an ionic compound that's soluble in water. It dissociates into sodium and hydroxide ions. There are other compounds, like molecular compounds that have OH groups, like methanol, CH3OH, that do not dissociate in solution, so they don't act as bases. Things like methanol are actually very, very weak acids. They have very weakly acidic properties because of the way that they are, but they're not bases. So these are typically going to be ionic with OH as the anion. Some sort of metal hydroxide, calcium hydroxide, sodium hydroxide, potassium hydroxide, things like that. In our Arrhenius definition are acids, which produce H+. Our acids produce H+, and our bases produce OH-. These things are going to combine to form water. which neutralizes them in the process. So we can neutralize acids with bases, we can neutralize bases with acids. That's what we're doing in our lab this week, is neutralizing acids and bases. The Arrhenius definition, unfortunately, doesn't cover all of our bases. It doesn't cover all of our acids. So some things don't contain OH minus, and they act as bases. So our Arrhenius definition doesn't work for everything. We need a better definition, a more expansive definition. We'll learn one pretty soon. The Arrhenius definition also doesn't apply to non-aqueous solvents. So if there's no water as your solvent, then it doesn't work. And so a better, more general definition is from Bronsted-Lowry. And I think they're Danish. Bronsted, I think, is Danish, and Lowry might be American or British. I don't remember. Doesn't matter. Under our Bronsted-Lowry definition, which is a more expansive definition, our acids are proton donors. What's a proton? Like what? How would we write that out? We could write it as P+. We could also write it as one of our elements. As an ion. Anyone? H+. So proton donor, it's giving H+. And then our bases are not defined based on their hydroxides. They are also defined based on protons. So these are things that can receive or accept H+. So our Bronsted-Lowry definition really centers protons. It really centers H+. If you're giving away an H+, you're an acid. If you're receiving an H+, you are a base. This often matches up with our definition for from Arrhenius. It's just a different way of thinking about it, and this includes things that Arrhenius doesn't. So again, we're focusing on our H+ ions transferring in acid-base reactions. So in solution, HCl is a Bronsted-Lowry acid. HCl has an H in front. We know it's an acid. It's an acid because in solution it donates a proton to water. So this is why that H3O plus is important. This hydrogen gets sent over to the H2O. One of those lone pairs goes out and grabs it, and it turns into H3O plus, and then the chloride is just left by itself. Secretly, it has an entourage of water molecules around it. But this is the way that we write it. And so this shows us really what happens to that H plus ion. It goes from the HCl to the H3O plus, how it actually exists in solution, and we get hydronium. It also works with bases that don't contain hydroxide ions but still produce, indirectly, hydroxide ions in solution like NH3 ammonia. NH3 also has a lone pair on it, and that lone pair can grab one of the hydrogens off of water. So if you put ammonia into some water, there's tons of water molecules in there, and sometimes those hydrogen parts pop off as ions, so you'll get a hydronium that just, or an H plus, a proton that just pops off. And if there's an ammonia nearby that can grab it, that can steal it away, then that is what happens. So instead of NH3, it goes to NH4 plus. So NH3 accepts a hydrogen, an H plus, from water. It doesn't actually just pop off by itself. That was I was thinking of a different thing. Accepts an H plus from water, which forms hydroxide. So the H2O loses its H plus, and now it's just OH minus. Questions about either of our definitions so far? We've got Arrhenius, produces H plus in an aqueous solution, or produces OH minus in aqueous solution. We've got Bronsted-Lowry. It's giving proton, it's receiving proton. Acid base. Acid base always occur together in our Bronsted-Lowry definition. And you may notice that we use water in both of those reactions. So water in the first one, the HCl was acting as an acid, it was donating that proton, and that proton had to go somewhere, and that somewhere was to water. So water received a proton, so water was acting as a base because it was receiving a proton. Base behavior. And we produce H3O plus in solution, that's why our HCl also represents an acid. And then in the next slide, NH3 accepted a proton from water, and so it was a base. It was receiving a proton, that's base behavior. And the water gave that proton. Giving a proton away is acid behavior. So water is acting as an acid, and we've got a special word for that, which is amphoteric. Things that are amphoteric act as a base or an acid, not in that order, by either accepting or donating a proton. I don't expect that that will be a big focal point, despite it being bolded. If we reverse the equation for the Bronsted-Lowry acid-base behavior of NH3, the ammonium, the NH4+, so we flip the left and the right side from the previous slide, the NH4+ can give that proton back. And this does happen in solution. So it can give one of those back. It says, no, thank you, I don't want it anymore. Gives it back to an OH minus that's floating around. That OH minus, because it's accepting a proton, base behavior, turns back into H2O. The NH4+ is giving away a proton to turn into NH3, and that's acid behavior. And so we refer to these two pairs, the NH4+ and the NH3, and the OH minus and the H2O. Those are two things that differ by just an H+. And we call those a conjugate acid-base pair. One is an acid, one is a base. We'll also see this on the next slides. So our conjugate acid-base pair, two substances related to each other by the transfer of a proton. So our NH3 and our NH4+ are an acid base conjugate, conjugate just meaning they're related to each other, pair. The NH3 is the one that acts like the base. The NH4+ is the one that acts as an acid. So in an acid-base conjugate pair, we've got something that behaves like an acid. We've got something that behaves like a base. And the only difference is that the one on the left has one fewer H's than the one on the right. The way that this works out is our base accepts a proton, because that's what bases do, and in turn it becomes the conjugate acid. An acid donates a proton, because that's what acids do, and in turn becomes a conjugate base. So we've got our H2O giving a proton to NH3 that turns into OH minus. These are an acid-base pair. One's an acid, one's a base. Our NH3 and our NH4 plus are a base and the conjugate acid, so they are a conjugate acid-base pair. The right side, the product side, is the conjugate side. So we'll call the thing that's on the right the conjugate, and then whatever it is, a base or an acid. The left side we just call our acids or bases. In a conjugate acid-base pair, you're going to use each of those three words for, not the pair part. You're going to use each of the other three words, the conjugate acid base. You're going to use each of those words one time. So base and conjugate acid, we've checked our boxes. Conjugate acid and base all got used. Acid and conjugate base, acid, conjugate base, conjugate acid base, all three words got used one time. As you might be able to tell, this is often confusing. That's why I'm talking about it so much. Also worth pointing out, the conjugate base is paired with the acid. It's not paired with the base, it's conjugate base, it's not conjugate to the base. Conjugate acid is an acid. It's not conjugate to the acid. It's the counterpart for the base. In these reactions, please identify the acid, the base, the conjugate acid, the conjugate base. I'll do it for the first one, and then I'll give us a little bit of time to do it for the second one. So we are looking for an acid, we're looking for a base, we're looking for a conjugate acid, we're looking for a conjugate base. Let's start off looking for the acid and the base. We've got two chemicals on the left side. One of them's got to be an acid, the other one must be the base. If you have an acid, there's got to be a base somewhere. Our acid is going to have an H in front. Both of these have an H in front. Water's even got 2 in front. So then we have to look at, all right, well, what do they turn into on the right side? And we've got C2H3O2 minus that's different from HC2H3O2 by an H. Moving from acetic acid on the left, the HC2H3O2, to the acetate on the right, what happened? What did we lose? Our H. Lost H plus. So this must be our acid, the HC2H3O2. That's our acid. The other thing that changed, the H2O turned into H3O plus. This gained H plus. Picking up or receiving a proton makes it a base. Changing my colors here. So H2O in this case is acting as the base. Then to the conjugate side. H3O plus is paired with the base. They differ by a proton. If H2O is the base, then the H3O plus must be an acid. This is our conjugate acid. If it goes from the right side to the left side, it would have to lose or give up one of these H's, go from H3O plus to H2O. Losing or giving away an H plus makes it behave like an acid. It's on the right side, which is the conjugate side. So it's an acid on the conjugate side. Our C2H3O2 minus is paired with our acid. We use each of those words, conjugate acid base pair, one time. We already used the acid part for the HC2H3O2. So the other part must be our conjugate base. Trying to cover the couple of different ways that we can think about it. Please identify the acid, the base, the conjugate acid and the conjugate base for B. We are rushing a little bit, so cut us off on time there. Hopefully we got that the CH3NH2 on the left side, it doesn't really look like much to us, probably, but on the right side there's a thing that looks like it that's picked up an extra H+. That means that this must have accepted a proton, an H+. Accepting a proton means that it's a base. The H2O is the other thing. It must have given the proton, or the H+. It went from H2O to OH-. So it did give away the H+. That makes it an acid. And on the right side, another thing that these examples have in common, which won't always be true, probably might always be true, I haven't checked. The positive thing is the acid, the negative thing is the base. So positive, that's our conjugate acid. The negative, that's our conjugate base. Hydroxide is a base, it's on the right side, that's the conjugate side, so we give it the conjugate label, conjugate base per OH-. Things that are on the left side, acid base. Things that are on the right side, conjugate acid, conjugate base. Sometimes you'll be shown a molecular equation instead of an ionic equation. And so instead of seeing CH3NH3+, there might be some counter ions. So instead of having this leftover plus charge, it might have a Cl at the end, which would hide the fact that it's a positively charged ion. The OH- might have a sodium in front. It might be NaOH, which would hide the fact that it's got this negative charge. That happens sometimes. You might be shown that sometimes. I don't remember if it happens on the homework, but there's, I think, an example problem at the very end. So what reactions can acids and bases go through? You might have been thinking to yourself. You probably weren't, but you might have. One of our reactions that we can do is neutralization reactions. So acid-base reactions generally form water and a salt. A salt meaning an ionic compound. Not always NaCl, which is what we call salt, table salt. So here we're producing salt, which is a salt. It's an ionic compound. Salt is just a generic term for ionic compounds. And they also form water. So acid-base reactions, neutralization reactions, acid plus base. Typically we get out water plus a salt. In this case, the chlorine, the chloride that produces in solution, and the sodium paired up to make our salt. It's aqueous, so if we were to do a net ionic equation or even a complete ionic equation, they'd be separated, Na plus Cl minus. In the net ionic equation, we take it out, and so our net ionic equation for acid-base neutralization reactions is this. H plus, acid, OH minus, base, go to produce H2O, which is water. You should memorize acid plus base goes to water and a salt. Sometimes these are also gas evolution reactions. So like this reaction that I did in my backyard. When you mix baking soda, sodium bicarbonate, and vinegar, it foams up. This is typically what's going on behind the scenes in those paper mache volcanoes that people do for science fairs. I don't know if people still do those for science fairs, so that might be a me being old thing. Let's say that we want to write a molecular equation, not complete ionic equation, not net ionic equation, for the reaction that occurs between aqueous carbonic acid and aqueous sodium hydroxide. Hint, carbonic acid, H2CO3, is a diprotic acid. There's two hydrogens in front. Two hydrogens in front means that it's diprotic. So we've got some things. We've got H2CO3. Our other reactant is NaOH. What's one of our usual products for an acid-base reaction? Water, which has the formula H2O. And you might want to instead write this as H-OH for balancing purposes. You might want to do it that way. What's one of our other usuals for products? A salt. And the salt is going to come from not the H, not the OH, the other thing. It's going to come from the sodium and the carbonate. Sodium is going to be Na+, carbonate is CO3 2-. If we crisscross these, we're going to need 2 sodiums to balance out. So this is going to be Na2CO3. So we're making water, we're making a salt. This is also a double displacement or double replacement reaction. So you can also make it move that way. We put the sodium and the carbonate together on the right side in our Na2CO3. We took the OH and the H and put those together in our H2O. This is part of why I wrote it out as HOH. So we can see separately the hydrogen that we got from our acid and the hydroxide that we got from our base. If we want to balance these out, we can do it like a double displacement reaction. We can start with something that's not the same on both sides. What's something that's different on the left versus the right? Sodium is a good one to start with. So we've got Na, we've got 1 on the left, 2 on the right. So we're going to need a coefficient of 2 in front of the sodium hydroxide on the left side. When we do that, what else changes? The hydroxide, the OH. Now, what if we didn't have H2O written out differently? If we have it just written as H2O, it becomes a little bit less easy to see that we've got hydroxide on the right side. That's why I recommend viewing this as an alternative HOH, because it shows us there's one OH in each H2O. So on the left side, we've got 2 hydroxides from our NaOH. On the right side, we've got 1 hydroxide. So to get that up, we had a 2 in front of our H2O, which doubles our OHs. It also doubles our H's. Now we've got 2 H's on the right side. We have 2 H's on the left side from our H2CO3. So 2 and 2. Last thing to check is our carbonates. It's 1 and 1. You can also do it other ways. You don't have to do it this way. I think that this way is nice. Another way that you might balance acid-base neutralization reactions is that we know that the OH and the H, those are going to find each other and make water. So we need an equal number of H plus and OH minus. We've got 2 H plus that are going to come off of this carbonic acid. We've got 1 OH minus that's going to come off of this NaOH. So we need a 2 in front of our NaOH to get those to balance out. A lot of the time we don't care about the products for these. So sometimes that's a nice fast way, get the H plus number to match the OH minus number, and then the part we care about is balanced. Not all the time, but a lot of the time. Other reactions that we can do with acids. Acids dissolve many metals, and the way that they dissolve these metals is that the metal reacts with an acid like HCl. It produces hydrogen gas, H2, and salt, a salt. So metal plus acid, it's going to dissolve to form hydrogen gas, H2, and also a salt that's made up of the dissolved metal and then the counter ion, the anion of whatever our acid is. Not all metals react with acids. So metal, acid, we're getting H2, we're getting a salt. We're going to get a lot of salt in our acid reactions. Acid base, acid with metal. There's also another one that we'll see very shortly. That's just a picture of some dissolving zinc metal. Acids also react with metal oxides. Metal oxides are a metal plus oxygen. When we had acid plus metal, we made H2, and we also made the salt, MgCl2. What's different about these metal oxide reactions? What changed? Instead of hydrogen gas, we have water. And on the left side, instead of our metal, we have a metal oxide. That oxide pairs itself up with the H2 gas. So now we get H2O instead of H2. So we're producing water instead of gas. So all that really changed, we add an O to our metal, we add an O to our hydrogen gas, and now it's water. It's our other type of reaction. Circle. I'm going to skip this, and we'll move on to base reactions. All you need to know about base reactions is there are base reactions. They're not that important. Yay. Questions so far? Do we remember electrolytes? We had strong electrolytes, weak electrolytes. What makes something a strong electrolyte versus a weak electrolyte? Okay. It is related to its conductiveness. So a strong electrolyte is going to dissociate completely. A weak electrolyte, you'll have some intact units remaining in solution. The strong and weak part of that also apply to our acids and bases, which is why I'm trying to tie a string back to that discussion about electrolytes. So hydrochloric acid, hydrofluoric acid look very similar. It's hydrogen paired with a halogen. However, HCl is a strong acid. It completely ionizes in solution. So strong means it completely ionizes in solution. HF, on the other hand, is a weak acid. It does not completely ionize in solution. So for HF, in solution, there are HF molecules floating around. Intact, whole HF molecules in the solution. With HCl, there is no HCl floating around in solution. It's all H plus and Cl minus floating around as ions. So strong completely ionizes in solution. Weak does not completely ionize in solution. So our strong acids ionize completely. You put HCl into water, it completely separates out. Strong acids are strong electrolytes. If you have a 1 molar solution of HCl, remember we talked Tuesday about ion concentration. We've got 1 H plus, we've got 1 Cl minus. So 1 H plus produced for every HCl, we're still going to have a 1 molar concentration of H3O plus. The brackets means molar concentration. Or just concentration, really. So our 1 molar HCl solution, all of these hydrogens release. Our H3O plus, which is the same as H plus, is also going to be the same concentration. Here are some of our strong acids. Strong acids that you should know are bolded. HCl is one that you should definitely know. I don't remember if I put sulfuric acid on the exam. I think nitric acid would be the other one to know. So I'll circle it, and we'll put an arrow at the H2SO4 because I think that's a little less likely to show up as a strong acid. The other ones are also strong acids. This is a table from the book. The other ones are also strong acids, so if you do some of the strong acid related homework questions, then those might show up. You'd be expected to just look up what are the strong acids. There are also weak acids, and weak acids do not completely ionize. They contain relatively few ions, because weak acids are weak electrolytes. So if we put HF into solution, we dunk HF into some water, that's worse. That's awful. The HF, we're going to have some intact HF in solution, unlike with our HCl that was completely split. Another sign that we might be dealing with something that's weak is this double arrow. That double arrow means the reaction goes left to right. It also goes right to left. So it's going both ways at the same time. It can go in the forward direction. It can also go in the reverse direction. And it's doing both. If it's a strong acid, it's just going to move in one direction. For our weak acids, we've got 2 weak acids that you should know. We've got hydrofluoric acid and acetic acid. Acetic acid is the one that we're using in lab this week. Hydrofluoric acid we're not using in lab this week. If you've seen Breaking Bad, you might know why. It's the one that they used to dissolve that bathtub in the first season. There are many weak acids. Most carboxylic acids are weak. These are the 2 that we care about, hydrofluoric and acetic. Generally, carboxylic acids are going to have this form H and then some sort of CHO part on there with subscripts. So H C2H3O2, HCHO2. Those both have that CHO set of letters in there. That's a sign that it might be a carboxylic acid. All right, we want to determine hydronium concentrations in solution. And you might be thinking to yourself, Mr. K, we can't figure that out. We can. It's ion concentrations. So we have to think about, when we're thinking about H3O plus concentrations, does it completely ionize or does it not completely ionize? Those are the two options that we have in this class. When you get to Chem 2, you can figure out the extent to which they ionize. So we can actually put a number to it if it doesn't completely ionize. We're not going to do that in this class. It's too much. HC2H3O2, is that a strong or weak acid? Weak. Why is it weak? CHO. Weak acid. That's one of the ones that you will be expected to know. So put that on your flashcard. If it's weak, does it completely or not completely ionize? Does not completely ionize. So we're going to have some leftover HC2H3O2 units in solution. If it completely ionized, it would reach this 0.80 molar concentration. Since it does not completely ionize, it will not reach this 0.80 molar concentration. So it's going to be less than 0.80 molar H3O plus. We don't know how much less than, just that it will be less than. HNO3, strong or weak? Strong, because it's one of the ones that we memorized. It doesn't have that CHO in there. So this is a strong acid. Oops, all ions. So HNO3 turns into H plus. We're also going to get NO3 minus. Before it dissolves, it's HNO3. HNO3. After it dissolves, we get H plus, which is the same as H3O plus. That's what we care about. What's our ratio between HNO3 and H plus? What's our ratio between the two things underlined in blue? 1 to 1. So if we take that 2.25 molar HNO3, we can use that 1 to 1 ratio. You might even be able to do that in your head. Why did I write plus? I meant 1, H plus on top, 1, HNO3 on the bottom. It turns out it's 2.25 molar H plus. It's the same concentration. That works because it's strong. If it was weak, it'd be less than that number. Because it's strong, it hits that number. It completely dissociates, completely separates. HF is also weak. So the HF concentration, the H3O plus concentration is going to be less than the 0.70 molar. It's weak, it doesn't hit that number. If it's strong, it hits that number. That's for acids. We also have bases. We've got strong bases. What's something that all of these bases have in common in the table? They have OH. And so you might think to yourself, oh, that's a strong base. Just like we had CHO, we've got O. Unlike our diprotic acids, which ionize in 2 steps, bases that have 2 OH minus ions dissociate in 1 step. So magnesium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide, they'll all dissociate in 1 step. Notice that we've got a 2 in front of our OH minus because we've got a subscriptive 2 from our calcium hydroxide. This 2 turns into a coefficient when it ionizes. NaOH is a strong base. We also have weak bases. Generally, our weak bases produce OH minus by accepting a proton from water. That makes the water turn into OH minus ions. There are many weak bases. Organic amines have nitrogen in them. Our 2 notable examples are NH3 and C5H5N. The nitrogen that's in there does the weak base behavior. Sodium bicarbonate can also act as a weak base. This is part of the reason that we have sodium bicarbonate, baking soda on hand in the lab rather than some other chemical, because we can neutralize acids, we can neutralize bases, and it's relatively cheap and it's very safe. For determining hydroxide concentration in solution, from bases, determining ion concentration is a little bit more complicated because we can have 2s. So for example, our calcium hydroxide that we've got in A, first thing we need to think about is it strong or weak? Strong. Why is it strong? Oh, that's a strong base. So we've got the OH in there telling us that it's strong. When this dissolves in water, when this separates in water, we're going to get out 2 hydroxides. We are trying to figure out the hydroxide concentration going from calcium hydroxide to hydroxide. What's our ratio for the blue underlined things? That's right, it's 1 to 2. So 0.135 molar CaOH2. Double it and keep it. Sometimes humor is subversive. So it's going to be 0.270 molar hydroxide. And number 2 is NH3, strong or weak? It is weak. It's got nitrogen. So our hydroxide concentration is going to be less than 0.95 molar. And then our last one, 0.50 molar, it's got that O, so it's a strong base. Water is amphoteric, and it will dissociate by itself in solution. So it does this. 2 waters get together. One of them decides it's going to bully the other one. We get an H3O plus, we get an OH minus. This is called self-ionization. It occurs, but to a small extent. In pure water at 25 degrees Celsius, the concentrations are equal because it involves waters transferring with itself. We don't get extra H pluses or OH minuses. And it's a low concentration, 1 times 10 to the minus 7 molar. We can calculate an ion product constant for water. That's our Kw. The W means water, and the K means that it's a constant. So this Kw is when we multiply those concentrations, and so the exponent adds. So it's 10 to the minus 14. in a neutral solution, our acid equals our base. Neutral is when acid and base are equal, perfectly balanced. Related to that, so our neutral solution, H plus equals OH minus at 25 degrees Celsius. In an acidic solution, we've got more acid, more H plus than base. In a basic solution, we've got more base than acid. In all aqueous solutions, we're always going to assume that it's 25 degrees Celsius. In all aqueous solutions, this is true. The H3O plus concentration times the OH minus concentration equals that Kw constant. This is one of our 6 acid-base equations. The key takeaways: acidic solution, more acid than base. It can be confusing because we're dealing with negative exponents. If you put them in standard notation, the decimals, you'll be able to see which one's bigger or smaller based on who's got more zeros in front. In a basic solution, we've got more base than acid. You'll be given this Kw equation. These two things are related. So in an acidic solution, H3O plus concentration is 10 to the minus 4. OH minus is 10 to the minus 10. If we express those in decimal notation, it's very easy to see the 10 to the minus 4 is much bigger than the 10 to the minus 10. In a basic solution, our H3O plus is 10 to the minus 9. Our hydroxide is 10 to the minus 5. We've got more base than acid. That's why it's a basic solution. For both of these, if you multiply these together, you'd get 10 to the minus 14. You can use this in calculations. So H3O plus concentration times hydroxide concentration equals Kw, which is 1 times 10 to the minus 14. Our units are going to be probably molar squared, but whatever. The H3O plus and the OH minus are going to be molar. If we want to solve for hydroxide, which is not what we want to do here because we're given hydroxide, we want to solve for H3O plus. This, to get it by itself, divide both sides by the hydroxide. So our H3O plus concentration is 1 times 10 to the minus 14 molar over 1.5 times 10 to the minus 2 molar. I'm going to put a squared so the units work out. As a reminder, in case we haven't done these in a while, in case we haven't been thinking about that dolphin key on our calculator, you can either enter in the times 10 to the power of. You need to use parentheses if you do that. Or you can use the little dolphin key, the double capital E's. It's got to be the capital E's. So this would be 1 little capital E minus 14 over 1.5 little capital E minus 2. Should look something like that on your calculator. We get out funny number times 10 to the minus 13 molar. which one do we have more of? Hydroxide or hydronium? OH minus or H3O plus? Which one of these is bigger? Times 10 to the minus 2 or times 10 to the minus 13? 10 to the minus 2 is bigger. So we've got more OH minus. Is OH minus acid or base? It's base. So this is basic. The calculations are the same for all these. It's also the same if you're going the other direction. So if we were solving instead for OH minus, we'd divide both sides by H3O plus. So the H3O plus would be on the bottom over here. So if we're solving for one of these, you just divide this 1 times 10 to the minus 14 by the other thing, and you get your concentration. Relatively simple in terms of like the actual math. A little confusing because we're dealing with negative exponents. But that's why we have the pH scale. So the pH and pOH scales are other ways that we can express acidity and basicity. On our pH scale, pH smaller than 7 is acidic, pH greater than 7 is basic, and a pH of 7 is a neutral solution. You might be thinking to yourself, what is pH? Don't worry, we'll get there. This is typically how we see acidity expressed. We've got some examples of things that are acidic and basic. Hydrochloric acid and lemon juice are both very acidic. Coffee, tomato juice, orange juice, soda, also acidic. Can wear down the enamel on your teeth. Things that are really basic, things like bleach, sodium hydroxide, ammonium solution. Somewhere in here is fancy water, volcano water from the store. That's also in there. That's usually a little bit basic. Ignore most of this slide for time's sake. If you want to come back and relearn logs, I've tried to lay it out in a way that makes sense. Logs are just generally confusing. The bolded part is the most important part. pH is negative log of H3O plus, which is chemically equivalent to saying log of H plus. The little p means negative log of. Just clarify that that's negative, not minus log of. So for pH, it's the negative log of H plus. We also saw POH in the header previously. That's negative log of OH. When you write logarithms in your calculator, you don't need to know how they work. You need to know that it has to be the one that says log. ln is a different thing. It has to be the log. It must be the log. If you've got my favorite, the TI-36X Pro, you have to press that button twice to get it to do log. If you press it once, it's ln. You'll get the wrong answer 100% of the time if you use the ln. That's natural log. It's using a different base, so it won't work. Let's calculate pH. You will also be given the pH equation. pH is negative log H plus. So we're putting into our calculator, our concentration is this 5.8 times 10 to the minus 4. Putting in the calculator to get pH, negative. On my favorite calculator, this is the negative that's between the parentheses, down by the period. And then we're pressing that log button twice. And then we're entering in, it'll give you a parentheses, we're entering in the 5.8. We're hitting that double E key. One time, we're doing another negative sign and a 4. So negative log 5.8 e negative 4. You should get out 3 point, it would just be 3 for sig figs, but whatever. We'll put 3.2. Don't worry about significant figures for pH stuff, because it's the number of decimal places is the number of significant figures, which is fun and confusing. So our pH is 3.2. Is that acidic or basic? Do we remember? It's below 7, it's acidic. Do we have questions about this, particularly the calculator entry part? You should get out 3.236572006. Shout out to people born in 2006. If you don't get this, ask me in lab, ask Logan in lab, ask one of us in SI sessions if we're there. Logarithms can also be undone by an anti-log. We're not going to show that today. The result that we get out of this is 10 raised to the negative pH gives you back the H3O plus concentration. You'll also get this on your information sheet for the exam. So if you're given the pH and you're asked for the H3O plus concentration, this is what we're doing for that. I would recommend when you're choosing your homework questions for a final homework set, make sure that you're choosing some that are acids and bases. Make sure you're choosing some that are aqueous solutions, so you're getting some practice with them. Calculate the H3O plus concentration of alkaline drinking water that has a pH of 8.87. So pH is 8.87. We're finding concentration of H3O plus. That means we're going to use this thing at the top. 10 to the negative pH gives us our hydronium concentration. We'll flip it left and right. H3O plus concentration equals 10 to the negative pH for us. That's going to be 10 raised to the negative 8.87. So you can put in 10 raised to the negative 8.87. And sometimes, like on questions like this, your calculator is going to be really annoying. And it's going to be a lot of zeros and then a 1 at the end. That happens sometimes. If you multiply it by 1,000, it'll show you what the numbers are. Just remember that the first number was that 1. You could also tell your calculator to convert it into scientific notation, which I don't have the time to go through. So 0. We got 1, 2, 3, 4, 5, 6, 7, 8 zeros. 1, 3, 4, 9 molar, or 1.349 times 10 to the minus 9 molar. Something that you should see when you're doing these problems, a check to make sure you're not doing things terribly incorrectly. Your pH number and your exponent number should be plus or minus 1 from each other. The pH will be a positive number, the exponent will be a negative number, but the magnitude, the size of them should be plus or minus 1 because of the way that logarithms work. If you're going from pH to H3O plus, if you're going from H3O plus to pH, they should be plus or minus 1. If they're not plus or minus 1, something went wrong, and you need to try it again. There's also the POH scale. Look at that, POH, negative log OH minus. It works the same as the pH scale. There's also something that you can create with this KW thing. And that thing, we'll just jump to the ending for you. pH plus POH equals 14. This is like our sixth of the acid-base equations. There's the KW one that we've got here in the middle. We've got this one. This is the log form of it. We've got the two forms going from POH to OH, from OH to POH. We've got both directions for POH. We've got both directions for pH. Those are the pantheon of 6 fundamental equations for acids and bases. You will also be given this on the exam. We're going to skip that. We're going to skip those. Buffers. Our last little bit of information. This is why conjugate acid base is important. Buffers contain significant amounts of a weak acid and its conjugate base. I'll probably skip buffers on the exam. The weak acid neutralizes added base. The conjugate base neutralizes added acid. We've got buffer systems in our blood. There's buffer systems in water. They're all over the place. Buffer systems resist pH change. So if you add acid, if you add base, the pH will go up by a little bit, not by a lot. So if we get a little bit of extra acid in our veins, if we get a little extra base in our veins, we don't immediately perish, which is what happens if your pH goes outside of a particular range. If it goes too low, if it goes too high, you die. They have different names for those scenarios. So acetic acid and sodium acetate. Sodium acetate is the conjugate base for acetic acid. When we add base, the acid reacts with the base and it forms some acetate. If we add acid, it reacts with the acetate from the sodium acetate and reforms some acetic acid. Because it doesn't completely ionize, we have some of this conjugate base floating around, and we still also have some of the acid floating around. So they're both in there at the same time. If you take Chem 2 eventually, you get to do calculations with these, and they're a little bit gross. And that's a visual example of how they work using AN as our acid. Which one of these is a buffer solution? Which one of these is an acid, contains an acid-base conjugate pair? An acid-base conjugate pair differ by what? What makes them different? An H+. So we're looking for some things that differ by an H+. All of these things are neutral. This is the scenario that I was warning us about 30 minutes ago, or 45 minutes ago, whenever it was. If we pick, okay, we've got an acid, let's ignore the other part. If we've got a base, we've got nitrogen in there, that's a base. We've got the change in the H pluses. We can ignore that part. This would be a plus. These two would be minuses. That would be a minus. So we're looking for an acid-base conjugate pair, weak acid and its conjugate base. HCHO2 has that CHO group in it. It's a weak acid. After it's lost the H+, it's CHO2 minus. That's a conjugate acid-base pair. That would be a buffer solution. HCl is a strong acid. It cannot be a buffer solution. Strong acids can't make buffers. This is a weak base and its conjugate acid. I think this one's technically also a buffer solution. NH3 and NaOH are not even related to each other. Can't be a buffer solution. Questions about the entire chapter of acids and bases? As a reminder, there are versions of me going through it slower in more parts on last semester's playlist. You can also go to 3A from previous semesters before that, the year before that, and they'll also be slower, more in-depth, because I was just faster the rest of the semester.